Hey guys, Mr. Osman here. Today we're just going to be going over some more of the skill builders that we haven't gotten to. Today's our remote day, so we just wanted to make sure we got through all of the instruction we needed to. All right, so we're just going to go over kind of just the solutions to what we didn't get to in class, and we'll cover some of the stuff that we did have in class as well. All right, so let's go ahead and start at the top, right? Number one. Find the amount that results from each investment. And so this is just using those investment equations that we have, right? And remember, those are, and I'll write them down for you guys. A is equal to P times 1 plus R over N raised to the N times T power. And then when it's continuous growth, we have A equals P times E to the RT. All right, so these are stuff we should really just get really comfortable using, right? So number one, $50 invested at 6% compounded monthly after a period of 3 years. All right, so we know the principal in this case is 50. We're solving for the amount. That's what we want to know. The rate is 6%, which is 0.06. The number of times it's compounded monthly, which means 12 times, and after a period of 3 years. So t in this case is 3. All right, so if we plugged all those values in, it would turn into 50 times 1 plus 0.06 over 12, all raised to the 12 times 3 power. All right, and we could plug this all into our calculator, and what we get is $59.83. Right, number two is a very similar problem, right? The principal in this case, though, is 500. Right? It's invested at 8%, so the rate is 0.08, and it's compounded quarterly, meaning it's going to compound 4 times a year. And then for a period of 2.5 years. So t is 2.5. Remember, time, this t variable here, it's always in years, right? Always. So plugging that into our equation, we would have 500 times 1 plus 0.08 over 4, all raised to the 4 times 2.5 power, and you end up getting $609.50. Number three is a little bit different, but only because we're going to be using our continuous equation, right? Because it's compounded continuously. So just like the last ones, right? Principal is $100. The rate this time is 10%, which is 0.1. And then time in this case is 3.75 of a year, so 3.75 years. Right, we would plug that in and we get 100 times E, all raised to the 0.10 times 3.75. So we end up getting $145.50. Right, now number four, I know we did in class too, so I'm just going to talk about it just a little bit. It's comparing if he had $100 to invest at 8% annual interest rate compounded monthly. How long would it take before it's 150? And then how long would it take if it was compounding continuously? Right? So in both cases, the amount is 150. The principal is 100. The rate is 8%, which is 0.08. And then the time is what we're solving for, right? And then obviously the n in this case, and I know I'm kind of running out of room here. Or I guess it would be lowercase, but still. The n in this case would be, it's compounding monthly, so n would be 12. Right, so just plugging these values in, right? A is 150, P is 100, that would be 1 plus 0.08 over 12, all raised to the 12 times t. So here we have to solve for t, right? So first thing we can do is we can divide this 100 over, and we do 150 divided by 100 is 1.5. When we simplify all of this, right, and I can even show you that real quick, just so you guys know. Right, if you do 1 plus, oops, sorry, wrong button. 1 plus 0.08 over 12, right, you end up getting this decimal, but you can change that to a fraction, and it makes it a little bit neater, right? So that's all they did there, is they just simplified what's in the parentheses. And we got 151 over 150. That's all raised to the 12 times t power. So now that we have it like that, we can convert it to our log form, and we get log base 151 over 150 rate of 1.5 is equal to 12 times t. We can divide 12 over, so this would just be log base 151 over 150 of 1.5 divided by 12. We get this time here, 5.085. Right, comparing that to the continuous one, right? The only thing that changes is instead of having this 1 plus 0.08 over 12, we have just e, and then instead of 12 times t, we have 0.08 times t. Because again, we're using our continuous equation. So we plug in all the values, we divide the 100 over, and when we convert it, remember it would be log base e, but log base e is just natural log. Right, so natural log of 1.5 is equal to 0.08t. We can divide the 0.08, and we end up getting that the time is just about 5.068. And remember, time in this case is years. All right, so moving on to number 5 here. How long does it take an investment to triple in value if it's invested at 6% compounded monthly? Right, and what we got to know, okay, if the original was P and we want it to triple, right, well, that's just 3 times P. So the amount in this case is 3 times P, and we know the rate is 6%, which is 0.06. It's compounded monthly, right, so N is 12, and we're solving for the time. So we would go 3p is equal to p plus, times 1 plus 0.06 over 12, all raised to the 12 times t. Right, these p's would cancel out because we can divide them over, right? And when we simplify this inside the parentheses, we get 3 equals 1.005, all raised to the 12t. And from there, we can convert it to our log form, right? So here's our base, log base 1.005 of 3 is equal to 12 times t. And when you divide that 12 over and you punch that into your calculator, you end up getting that it's about 18.36 years. All right, so now let's go over some of the problems that we just watched the ad puzzle for, right? The exponential growth and decay. Right, and the interesting thing about this is if we remember our equation for exponential growth and decay, it's actually the same as our continuous compounded continuously equation. Right? It uses the same equation, A equals P times E raised to the RT. Right? So let's look at this. Number 6. The size P of a certain insect population at time t in days obeys the function P of t is equal to 500 times E raised to the 0.02 times t. So this right here is already in the form that we're going to use, the equation, right? A equals P e to the RT. Right? One big difference between this one and the one we use for compound interest is that t in this case it doesn't have to be years. It can be, in this case, it's in days. So it's kind of whatever the question is asking for. So if we want to know what's the initial population, that's asking what is our P. In this case, it would be 500, right? So it's starting with 500 insects. What is the growth rate? Well, that's this number right here. right? 0.02, well, that's just 2%. C is asking what is the population after 10 days? All right, so now we're actually going to be plugging some numbers into this equation. We want to know what is P of 10. Well, after 10 days, all we would have to do to solve that is plug in a 10 for T. So it'd be 500 times e raised to the 0.02 times 10. And when we plug that into our calculator, you get 610.70 insects. But really, we know we can't really have a fraction of an insect, right? So we can round that up to 611 insects, right? And then D is when will the insect population double? So if we're starting with 500, it's asking when is it going to be 1,000, right? So we would divide this 500 over. We get 2 equals e raised to the 0.02t. Sorry, I know this is kind of a little faded, but that's okay. Here we can convert it to our natural log form, right? Because log base e is just the natural log. We would take it of 2 is equal to our exponent here, 0.02t. We can divide that 0.02 over, and we end up getting that it's going to be 34.66 days, roughly. And remember, the unit's days because it's asking, or a question, it gives us that it's days. All right, so let's keep going. Number 7, a culture of bacteria grows continuously. 500 bacteria are present initially, and there are 800 after 1 hour. What's the rate of growth? All right, so here we know that the amount it grows to is 800. It starts with 500. And then the time in this case is 1 hour. So we're going to have 800 equals 500e raised to the 1r. We can divide this 500 over, we get 1.6. We can convert it to our natural log. And in this case, because the time was just 1, right? 1 times r is just r, so we don't have to divide our natural log by anything. We end up getting that it's 47, roughly 47%. Right? So B is asking if N is the number of bacteria and T is the time in hours, express N as a function of T. And pretty much all it's saying is now that we have the rate, right, what is our equation, right? Remember that A equals P times E to the RT. What is that equation in terms of, in this case, N is the number of bacteria, right? N turns into our A here. This is N of T is equal to our initial population, which we know is 500, times E raised to the rate, which is 47%, times time. Right? And that we can use for the next part here, C, how many bacteria will be present after 5 hours? Well, if we just plugged in 5 into our equation and we multiplied it all out, we end up getting that there's going to be 5,243 bacteria present. Right, so let's talk about decay, right? This has all been growth, so we've had a positive rate, right? But let's talk about when we have a negative one. Okay, iodine-131 is a radioactive material that decays according to the function A of T is equal to A naught E raised to the negative 0.087 T, where A naught is the initial amount present and A is the present amount at the time T in days. Assume a scientist has a sample of 100 grams of iodine-131. It's asking, what is the decay rate of iodine-131? Well, if we look at this equation here, right, the rate that it's changing is this negative 0.087, meaning it's kind of decaying, it's going away at a rate of 8.7%. B is asking how much iodine-131 is left after 9 days, round to the nearest thousandth, right? So we just got to plug in the values we know. We want to know how much is going to be there after 9 days. It starts with 100. The rate is this negative 0.087, and then the time in this case is 9 days. So we can plug all of this into our calculator, multiply it out, and we end up getting, there's going to be 45.703 grams. Right, so what about C? When will 70 grams of iodine 131 be left? Round to the nearest thousand. So this time it's giving us the amount, right? The after amount, 70. And we still have the initial, which is 100. And the rate didn't change at all. It's still negative 0.087. So we can divide this 100 over. 70 divided by 100 is 0.7. And then just like in previous problems, right, we convert it to that natural log, right? Because log base of E is natural log of 0.7 equals negative 0.087 times T. And then from here, we would just divide that over, and we end up getting that the time is roughly 4.100 days. All right, and then D, what is the half-life of iodine 131? Round to the nearest thousand. Well, we know half-life, it's exactly what it sounds. When is it going to decay to half of what's left? All right, so it starts with 100. When is it going to be 50? Well, we can divide that 100 over, just like we kind of divided over here. We get 0.5 is equal to E raised to the negative 0.087t. Convert it to our natural log, just like we did in the last problem. Divide the negative 0.087 over. And in this case, we get T is roughly 7.967 days. All right, so this is the half-life of iodine 131. This is how long it takes for half of it to decay away. Let's look at the last one here, number 9. This time it gives us the half-life. The half-life of radium is 1,690 years. If 20 grams are present now, how much will be present in 50 years? Do not round until the end of the problem. Round to the nearest hundredth. Right? So in this case, what we have to do is we have to use the half-life to figure out what the rate is. Right? So we know that 20 grams are present right now. In 1,690 years, half of it's going to be left, so 10. We want to know what is our rate, right? How much is it decaying by? Well, we can divide this 20 over, we get 0.5 is equal to E raised to the 1,690R. Right? We can convert that to our natural log form, and then divide by the time here, which is 1,690. And we get that it's roughly negative, the rate here is negative 4.1 times 10 to the negative 4th. Now, this is rounded out. If we look in our question here, it says do not round until the end of the problem. So what we're going to use is this rate, right? That ln of 0.5 all over 1,690. We're going to plug that into our next equation where it says how much will be present in 50 years. Right, so this time the time changes. It's 50 now. We're still starting with 20. And then the rate in this case is this natural log of 0.5 over 1,690. So we can just plug all of this into our calculator, right? We can do 20 times E raised to the 50 times natural log of 0.5 all over 1,690, right? And I can even show you that, right? I like to start with the E because it's got the exponent, which means we have to do it first, right? So we can say E raised to the 50 times, and let's see if this works, right? Yeah, this is supposed to be times, not minus. 50 times the natural log of 0.5 all over 1,690. Okay, and we get this long decimal here, but that's okay because we're just going to multiply it by 20. And we end up getting just about 19.59 grams. All right, thanks for hanging out, guys. If you have any questions, feel free to reach out to us.